what we're going to work on today is what's called implicit differentiation. Every function, guys, that we have talked about finding the derivative for have already been solved for y. So every equation that you have found the derivative for have been in the form of y equals, or f of x equals. If you think about all the different functions that we have in algebra, not every equation is very easily going to be solved for y. So when you're taking the derivative of a function, you're always taking it with respect to some variable. So when you're doing your differentiation, for example, we've strictly been doing dy dx. We've been taking the derivative of our dependent variable with respect to our independent variable dy dx. So when we do that, that's called an explicit equation, or we've been doing explicit differentiation. Explicit differentiation is when you simply have already got the equation solved for y, and then on the other side of the equation I write my y prime or I write my dy dx. Because what you're actually doing is you're taking the derivative of y, which is 1, and you're multiplying it by a dy dx. I haven't really gotten into that because we haven't talked about implicit differentiation yet. So the trouble we run into when we're working on derivatives is how are we going to take the derivative when the equation cannot be solved for y very easily? This is where we're going to use what's called our implicit differentiation. So when you have your variables x and y that are mixed up on one or both sides of the equation, it is called an implicit equation. So what has to happen when this occurs, you're going to have to use what's called implicit differentiation. So really, it's still the same rules that we've been doing, but what happens is as simple as this. When you are taking the derivative of a term that has y in it, you're going to have to multiply it by a dy dx. And then what happens is we'll end up solving for dy dx in the end, versus solving for y in the beginning, then taking the derivative. All right? So really what you're doing is you're taking the chain rule when you have a y. So again, we know the derivative of x is 1. We know that. When you're taking the derivative of y, we know the derivative of y by your power rule would just be 1, but it's going to be 1 times y prime. The derivative of y is just y prime, 1 times y prime. The derivative of x squared is 2x. So if you want to differentiate a term that has a y in it, so for example, if you want to take the derivative of y squared, again, you're taking the derivative with respect to x. It would be, again, applying the same rules we've been doing, so this would be your power rule, 2y, but because you're having to do your implicit differentiation, it's going to be times y prime, or times dy dx. So that's all implicit differentiation is. So for example, here's a curve, x squared plus y squared equals 4. So what's going to happen is you're going to take the derivative of both sides of the equation. This equation is not solved for y. So anytime you do not have an equation in the form of y equals, you're going to be using your implicit differentiation. You're going to differentiate both sides of the equation. By the way, what does this represent graphically, this equation? A circle. It's a circle. So I'm going to go ahead and find the derivative of this particular equation. So what is the derivative of x squared? The derivative of x squared is 2x plus. You differentiate y squared just like you did the x. What would the derivative of y squared be? 2y, but it's going to be times your dy dx, or y prime. So anytime you differentiate a term that has a y in it, again, you're using your implicit differentiation, you will tack on that dy dx. Equals. Don't forget to differentiate the right-hand side of the equation. What is the derivative of 4? 0. Now, what you're going to do is you're going to solve for your dy dx. So how would you isolate dy dx? What would be your first step? Subtract 2x. So I have 2y is dy dx is equal to negative 2x. Then what? Divide by 2y. So dy dx is equal to negative x over y. So now when you're using your implicit differentiation, notice the derivative may actually also contain a y variable in addition to the x variable, and that's fine. That's your implicit differentiation. What you're solving for is the derivative. You're solving for the dy dx. All right, so this is your implicit. So implicit differentiation, you're going to end up having y's and x's in the formula for the derivative. You still use it to find the slope. You're still using this to calculate the slope of tangent lines. But what would happen is you would not only have to plug in the x value, you would have to plug in the y value if you've got a derivative that has both the x and the y. All right? So now it's asking me to draw a sketch of the curve. Again, we just talked that this was a circle. Where's the center of this circle? The center is where? It's at the origin, 0, 0. And what's your radius? Your radius is equal to what? 2. So again, I know my center is at 0, 0. Radius of 2. So here's a sketch of the circle. Okay. So now what it's asking me to do in part C, it wants me to evaluate the derivative of x squared plus y squared equals 4. It wants me to evaluate it at x equals 0. So again, I already know what my dy dx is. I found that in part A. dy dx is equal to negative x over y. So now, again, like I mentioned to you, it's not enough to just know the x value. You've got to know the y coordinate as well. So again, what's the y coordinate going to be? Again, you've got to take 0. Where am I going to plug it back into? I'm plugging it back into my original curve. So I've got to find y first. So 0 squared plus y squared is equal to 4. So when x is equal to 0, what's the y value going to be? Plus or minus 2. So when I go ahead and I plug in 0 for x, again, I end up with, so I'm going to go ahead and do my point 0, positive 2 first. I end up with negative 0 over 2, which is just plain old 0. Would I also get the same value if I plugged in the negative 2 for y? Yes. So the value of the derivative is going to be 2. So if you jump down to part E, it wants me to illustrate the slopes for C and D. So again, I found the slope. When I calculated the value of the derivative to be equal to 0, what kind of tangent line are we going to have at the point 0, 2, and 0, negative 2? It's going to be what kind of line? Horizontal tangent. And you can see that from the circle. You can see that you're going to have horizontal tangent lines not only at 0, 2, but at 0, negative 2. Okay. Any questions on that? So now part D, same kind of question, except again, it wants me to evaluate the derivative at x equals 1. So again, since my derivative contains an x and a y, before I can evaluate this derivative, I've got to figure out what the y coordinate of the point is going to be. So when x is equal to 1, I have to plug 1 back into my original equation. So 1 squared plus y squared equals 4. So y squared will be equal to 3. So what's y going to be equal to? Plus or minus square root of 3. So you're going to have to evaluate it 2 places. At x equals 1, you have positive square root of 3. When x equals 1, you have negative square root of 3. So now what I want to do is I have to evaluate this derivative at 2 places. 1 square root of 3 and 1 negative square root of 3. So when I plug this in, I end up with negative 1 over square root of 3. So now I also have to evaluate it at 1 negative square root of 3. So I end up with negative 1 over negative square root of 3, which ends up being positive 1 over square root of 3. So what happens when you look at the picture, here are your 2 points. You have 1 positive square root of 3, which is 1 point on the circle. You have 1 negative square root of 3, which is another point on the circle. Because what happens with some of these equations, graphically, notice at x equals 1, you have 2 different y values. So what happens, notice if I sketch the slope, if I sketch my tangent line at x equals positive 1 positive square root of 3. Notice the slope of my tangent line. The slope of my tangent line is what? It's not positive, it's what? Negative, which is what I got right here. However, at 1 negative square root of 3, when I sketch the tangent line, what happens with the slope of that tangent line? That turns out to be what? Positive. So that's why you end up with, at x equals 1, you're ending up with two possibilities in terms of the slope of the tangent line. Two different values of the derivative. Because there's two different points on the curve that have an x value of x equals 1. That's what's going to happen. Again, this is what happens when you have to take the derivative of a function of an equation graphically that's not a function. It's failing your vertical line test. This is not a function. But you still have to be able to find the derivative and look at the slopes of those tangent lines. So any questions on A through D? Okay? So let's look at another one. So let's take a look at finding dy dx by implicit differentiation for the cosine of y squared equals x times y. So here's an illustration where we're not going to be able to even take this equation and solve for y. So look at, first of all, you have to take the derivative of both sides of the equation. So again, we're going to differentiate both sides of the equation. So let's work on the left-hand side first. Cosine of y squared. So what rule, actually, are we going to have to use in order to differentiate cosine of y squared? Chain rule, exactly. So again, our function is cosine. So what is the derivative of cosine? Negative sine. Y squared times. Now look at the derivative of the inner function. What is the derivative of y squared? 2y times your y prime or dy dx equals. So now, how am I going to differentiate? Be careful. How do you differentiate x times y? I said a very key word in there. Big figgy, product. Don't be fooled. X times y is not just taking the derivative of x and multiplying it by derivative of y. You still have to remember your product rule. So again, your fig figgy, f prime g plus fg prime. So f is x, g is y. So what is f prime then going to be? F prime is going to be what? 1. What is the derivative of y? Y, it's going to be 1 times your y prime or dy dx. So now I'm going to plug everything into my product rule. F prime, we told me, was 1 times g, which is y, plus f, which is x, times your g prime, which is your dy dx. So any questions? So really no rules have changed except when you differentiate a term that has y in it, you need to remember to show that you're doing the implicit differentiation by multiplying it by a dy dx. So now you want to solve for dy dx. So how are we going to solve for dy? Remember, you're not solving for y, we're solving for dy dx. You have a term on the left that has dy dx, you have a term on the right that has dy dx. So you want to make sure you gather all of your terms that have a dy dx on one side of the equation. So we have negative sine of y squared times 2y dy dx minus x dy dx is equal to y. So the only thing I did at this point was I moved that x dy dx to the left-hand side of the equation. Now what can you factor out on the left-hand side? You can factor out a what? Yeah, that's what you're trying to solve for. So now you can factor out the dy dx. So when you factor out dy dx, that leaves me with a negative sine of y squared times 2y minus x is equal to y. Now, how are you going to isolate dy dx? You're going to do what to both sides of the equation? Divide by the parentheses, exactly. So dy dx is equal to y over negative sine of y squared times 2y minus x. Yes, these derivatives are not going to be the pretty derivatives. They're not going to be the prettiest. But if you look at why we have to use the implicit differentiation, the original equations that we have to differentiate are not the prettiest either. All right? So you're not going to get the prettiest derivatives that you may see. All right? So any questions on example 2? Okay? Let's take a look at this next example. So one thing when you're doing your implicit differentiation is if you want to evaluate the derivative at x equals 1, you don't need to solve for the dy dx first. In other words, it may be simpler to go ahead and plug your numbers in and then solve in the end. So in other words, instead of solving for dy dx in terms of the variables, plug the values into the derivative, then worry about solving for dy dx. So first of all, I want to evaluate dy dx at x equals 1. So first of all, I'm going to have to take the derivative of both sides of this equation. So go ahead and see if you can do your implicit differentiation and find this derivative for me. Don't worry about solving for dy dx.